Here's another example for curve sketching. And what we're going to do is like we did before, we're going to find just the zeros. I can set x to the 5th plus 1 equal to 0 to find out what my zeros are. Sometimes it's really difficult to do that, and I don't expect you to do that if it's some complicated function, polynomial function that doesn't factor easily. It's okay to not do this part, but if you can do this part, you should do this part. This is easy because the 5th root of -1 is just -1, which means that this does have a 0, in other words, an x-intercept at x equals -1. And now I'm just going to take my derivatives. My first derivative is going to be 5x to the 4th. And when I set that equal to 0, I just get x equals 0. My next step is I'm going to take the second derivative, and that's just 20x to the 3rd. And when I set that equal to 0, I also get x equals 0. So it looks like my inflection points and my maximums and minimums might be the same point. And then I make my table. My table is going to be point/interval. And then I've got f prime, f double prime, and I write C for conclusion because it's easier to write C than to write the whole word conclusion. And if you don't know yet by now that I like to write things as short as possible, then perhaps we have never met. It looks like we have just 0. This is the only interval we're looking at. -infinity to 0, what's happening at x equals 0, and everything after 0. So we actually only have 3 rows for this, which is really nice. And then I can evaluate. So when x is less than 0, so let's say -1, if I plug a -1 here, it's going to be positive no matter what. If I plug a -1 here, it's going to be negative. When I plug 0 in to the original function, I get 1, positive 1. If I plug it in to the second function, I get 0. Sorry, the derivative, I get 0. And if I plug it into the second derivative, I also get 0. And then if I pick some number bigger than 1, bigger than 0, like say 1, if I plug 1 into the first derivative, it's positive. And if I plug it into the second derivative, it's also positive. What does all this mean? This means here that we are positive, we're increasing, but concave down. Increasing concave down looks like this. Looks like half of a parabola, like that. If everything is 0 here, and actually I can see that we're going from negative to positive, second derivative is going from negative to positive, I know I have a point of inflection at 0, 1. That's a point of inflection. And then they're both positive. Both the first and second derivative are positive, which means we're increasing and concave up. Increasing concave up looks like this. It looks like the second half of a regular parabola. And what I noticed from this is that this function has no relative extrema. It has no relative maximums or minimums because there's no place where the first derivative is 0, which would indicate a maximum or minimum, but the second derivative is either positive or negative because when the first derivative is 0, so is the second. And so I'm going to plot these points. I've got 0, -1, that's my x-intercept. I've got 1, 0, which is up here, that's my point of inflection. And I notice that I'm concave down to the left of it and concave up to the right of it. And so that's my function. It's a 5th degree polynomial. It's concave down here and concave up here. I'm going to do another example, and that will be in a separate video.